Gen Chem 2, isn't this exciting? I love it. Let's continue. Okay, what did we just learn in the last video? We just got so deep. Don't y'all feel like real chemists right now? We just got so deep with our reactions. What we learned is that in our collisions, in that collision, when we have learned anything second order and up, we have to have collisions in our molecules. And we learned that not all collisions are productive. In fact, we've got two major ideas here that have to line up in order for our collisions to be productive. We have to overcome something called activation energy, and we have to have the right orientation. So in Organic Chemistry 1, we're going to learn an SN2 reaction. It is second order, and it turns out we've got compounds like this, where we'll have something smack into literally a collision. Now this is a salt, let's put that up there. And our little electrons here are going to smack into this carbon. Specifically, they have to smack the carbon. This is our bond that's going to break. Not only do they have to collide with that carbon, they have to collide at a 120-degree angle to hit the right antibonding orbital. So no wonder we have millions of collisions with only a handful that are productive, because we have to have a collision with the right activation energy at that specific angle to actually make our product. And then we learned how to draw those and how to draw them on an energy diagram. So we would have, let's draw both examples of endo and exothermic, and let's include what a catalyst does. So let's draw us nice two energy diagrams. So what if we start up here with our reactants? This is our change in energy. And it's an exothermic process. That means we need to end down here with our products. That activation energy is a hump in between. Okay, so that is here. That is our activation energy. And then in our thermo, this is that change in energy that tells us this is exothermic. And then what does a catalyst do? Let's color code that. Our catalyst lowers that activation energy. Okay, perfect. So then how would you draw this for endothermic? Well, endothermic means your reactants are going to start lower than your products. There's still a hump to overcome, but then you end up here. And every once in a while, you can have multiple kind of humps in there, or you can end up like that. It just depends the level of that activation energy, but it is still there. And a catalyst can still help that process. Okay, so all of that is still there. You're just ending your products higher in energy than your reactants. So this part is the part that tells us it's endothermic. Okay, I love it. All right, now there are two equations, because wouldn't it be awesome to actually calculate that activation energy? All right, there's two equations to do that. And then I'm going to up the ante a little bit. Wouldn't it be awesome if we could also calculate how our rate constant changes with temperature? Remember, we focused an awful lot on rate and concentration in our previous units, which was super fun. We learned so much. That's how we got the order of our reaction. But then we kind of left temperature alone. But temperature has a huge effect on our rate. So this is how we're going to correlate what temperature does to your reaction. We can correlate our rate constant with temperature, and they do change. So we're going to correlate both of those. Let me give us two equations. These you're going to want to write on your cheat sheet. Okay, we're gonna take, wait, don't write the number 1 yet. We're gonna take what we ended our last video with and we're gonna rearrange it into something pretty usable. So let's just do a refresh on this one. Okay, refresh. And then let's turn that into something usable. So number 1, we're gonna turn this into something that would give us a linear plot. Shut the front door. Aren't we super excited to do another linear plot? So if we rearrange, we could do the natural log of k. Like that. Okay, now actually, if you're not excited by another plot, you should be, because calculating this way means that we can just let Excel do all of the work and we don't have to calculate anything. But in order for this to work, we have to plot the natural log of k and the inverse of temperature. So what are we looking at? We need to look at a plot of the natural log of k versus the inverse in temperature. Now, because we're using a gas constant, your temperature must be in Kelvin. Okay, mark that down. That's a pretty common mistake. And then it's also possible to just literally calculate 2 rate constants at 2 different temperatures. So we could also just use this to compare 2 sets of data. So we could take the natural log of 2 of these. And compare 2 temperatures. And we're going to do examples of both of these. Okay, so we'll start with number 1. I've given us some data here in a second. And then number 2, we'll write out a nice, just teeny little data set and we'll calculate both of those. It'll be super fun. All right, so let's start with that first one. What we're really looking for then is a set of data that has rate constant and temperature. And then what we're going to solve for, so I've got here, so this is the place where you want to pause and you want to go ahead and enter these on Excel or your calculator. And we're going to do just like we've done in the rest of our videos, and we are going to plot this data set. But first we need to get that entered in. We're going to monkey with it and then we're going to plot it. So whichever you feel comfortable with, take a second, pause the video now, and enter your data. Okay, once you've entered your data, this is exciting. So we've entered our data, and then we need to monkey with it. We can't just leave it like this because remember, what are we going to plot? We're going to plot the natural log of our k, and we need 1 over t, and our t needs to be in Kelvin. So we've got to do a little bit of work with your plot. We've got to take that k and get to the natural log. And we've got to take that temperature, convert it to Kelvin, and then do the inverse. So we learned how to do that in our last videos, and we can try one of these in class on Wednesday as well. But you can definitely use the math functions on your Excel in order to do that. So you don't have to do each one of them by hand on your calculator unless you want to. But let's take this bigger data set and then let's highlight the 2 columns that we're actually we're gonna plot. We're gonna plot these 2. So we've got to get to that. And then if you haven't converted temperature, that should say Celsius. I guess I got a little overzealous there. If you haven't done this calculation in a little while, remember that's 273 to go from Celsius to Kelvin. Okay, so now we're grooving because we've already done this in the last set of videos for our integrated rate law. Thank you, brain freeze. Okay, let's plot then. So we're going to do the exact same thing. You're going to click on a data set, click on one of your data points, and you want to check linear regression. You're going to do a trend line, and you're going to check display equation and display R value. So you want to add a trend line. Check that you want to display the equation and check that you want that R squared value. Okay, look at our R squared is pretty close to 1. We learned that with integrated rate law. That's awesome. And then check this out. Here's our slope. And our slope is how we're going to get to that activation energy. Okay, brilliant. Brilliant. I love it. Okay, so let's bust out that equation then. And let's figure that out. So our slope then from our equation was actually minus our activation energy divided by the gas constant. Okay, now we're going to use a different gas constant than we used in Gen Chem 1 because we need our energy in our unit. So let's write this one down. We'll always use this one for this equation, so you can write this on your cheat sheet. Notice my units, they're going to be in joules per Kelvin mole. And we need this one because don't we want energy? We're calculating an energy and our temperature is in Kelvin. So we're going to take that slope and we're going to rearrange. I'm going to go ahead and rearrange that our activation energy then is minus our slope. So our activation energy is minus our 8.3145 joules over Kelvin mole times our slope. Okay, I love it. And our slope is going to be in Kelvin. So go ahead and bust out your calculator, and what do you get? I get, okay, I'm going to round a little, joules per mole. Let's go ahead and highlight that. That is your activation energy. So really, kind of like our last integrated rate law series, really the hard work is done by Excel. Put in your data, get your linear plot, and here's your activation energy. That's awesome. Okay, that's awesome. Let's do an example with the other equation, and then we'll call it a day, and we'll try some of these in your homework. All right, so our second method then is what if you just have a data set where you have two temperatures, oh my goodness, excuse me, two temperatures and two rate constants. So let's say at 550 degrees Celsius, oh, let's actually write that. The rate constant is 1.1 liters over moles times seconds, which is really 1 over molarity. Okay. And then what if we look at a second temperature? How about 625? We go a little bit hotter and we recalculate K, and it is 6.4. Okay, done. Can we calculate activation energy? Absolutely. So this is where you can actually do this without a plot. We're going to use that second equation, and let's write that out again. That's the natural log of your two rate constants. Okay, and then we're going to compare those two temperatures. Now I'm going to put a little star here. You can see this rearranged occasionally, and different textbooks may have these swapped, but then they're also going to have these swapped. And then you may or may not have a negative there. So really, they're all the same. They're just rearranged. All right, so once we get to this, honestly, isn't this a great way to end kinetics? Because it's really just plug and chug. It's kind of like our gas laws. Here's our two Ks, here's our two temperatures. Let's just write it out and calculate it. So I'm going to go ahead and take this. My activation energy, that's what we want. I'm going to go ahead and put our gas constant right in there. And let's compare those two temperatures. Okay, no, wait a second. Can I just put 550? No. You have to convert to Kelvin. Remember, we had to do that in our data set. Okay. Holy cow. All right, let's rearrange all of this for our activation energy. Bust out your calculator and let's see if we're matching. Whew. All right, let's see what we get for activation energy. You try it, I'll try it, and we'll see if we get the same thing. That is what I'm getting. Awesome. All right, this is a great place to stop kinetics, and now we can just apply in class.